Okay, welcome to Robotics 1. In today's class, we are going to talk about velocity analysis. So, grabber joint isn't the end effector, but a revolute. Yeah, the end effector is at the end. So, basically, when you try to solve the inverse kinematics, you will realize that the grabber arm affects the orientation. So I would include that as the part of the forward kinematics. But when you do the inverse kinematics, you will have to split it to find the appropriate orientation. How can describe the amount of freedom when it changes based on the position? So I'm not really sure what this question means. How do we describe the amount of freedom when it changes based on the position of other arms? So maybe after the class, I will try to call you and try to answer this question or understand this question better. Okay, in today's lesson, we are going to talk about the differential motions. Now, differential motions are the teeny tiny motions. So in this chapter, there are actually two important concepts. First important concept is how do we find out the velocities, the linear velocities of the end effector or linear velocities of various limbs or joints, and how do we find out the angular velocities of various joints. And the second thing is how do we find out the Jacobian. What do we mean by a Jacobian, and how is this Jacobian calculated? So there are two key points in this chapter. So key points. So the first point is how to find linear and angular velocities. That is the first question. And second question is what is Jacobian and how to find it. So these two questions are the theoretical discussion part, and then we will work out the problems. And I will try to explain the problems based on what we have learned so far. So it will not be something totally new, but sort of the extension of the material that we discussed. Now, first and foremost, I want to discuss the concept of differential. So the first thing is, what do I mean by differential? So differential, if you loosely look at the definition, is nothing but the derivative. So for an example, you must have seen that if you have, say, 2x, f of x is 2x, and df of x by dx is equal to 2. Or for that matter, if you say f of x is equal to x square, and then what you do is you want to find out df of x by dx, which is the derivative, which is 2x. Now, if you think about mathematically, what does this mean? It means a small change, small change. And let's try to visualize what this means. So for an example, if I have function f of x on y-axis, and if I have the x, the value on x-axis, and if I want to plot this function, f of x is equal to 2x. So the function that I'm trying to plot is this. Now this function can be shown to be a straight line. So this is nothing but a straight line. So f of x is equal to 2x. If I want to find out the slope of the line, I take the ratio. This is delta y divided by delta x, and you can see that this slope is equal to 2. Now, this simple exercise tells me an important finding. The important finding is this. If I am at location, say 1, if I am at location 1, and if I want to go to location 2, if I'm at location 1, if I want to go to location 2, what I could do is I could multiply the slope by the distance traveled in the horizontal direction. So I could multiply slope by the distance traveled in horizontal direction. I'm going to call that x2 minus x1. And I can find out the value of the function at point 2. So what this simply means is f of 2 is equal to f of 1 plus the slope times delta x. And this is an important observation. And this is applicable for not only a quadratic function or a cubic function, and we are going to use the same concept in robotics. So what do we mean by differential motions? Differential motions are defined as small motions. Differential motions are small motions. And these small motions are super important because, as you know, a journey of 1,000 miles begins and continues with one step at a time. So you start the first step. So essentially, if you want to travel a long distance, you would be taking teeny tiny steps multiple times and try to reach to the destination. Now, if you take a look at the differential motions and then divide those by time intervals, you get velocities. So let me give you an example of what this means. Say if you have, let me show you a path on X and Y graph. So for an example, this is the path on X and Y graph. So what I want to show you is you are going from point 1. So, or we are going from the initial position to the final position, say A. And at every location, I can sort of approximate this path as a straight line. So what I could do is I could say go straight line here, 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 go straight line here. And if I have this straight line approximation, it can be noted that over a teeny tiny period or over a small region, So over a small step, this curve can be approximated as a straight line. And this is an important observation, because what I could do is, if I want to go from point point O to point A, I could actually make these small changes in my path and get to the final destination. And that is what it means by differential motion. This differential motion is a teeny tiny change in the position, and if I divide this teeny tiny change in the position by the time it takes to carry out that change, I get the velocity. So differential motions are teeny tiny motions, and when I divide these small motions by the time, so it is something like dx divided by dt, or delta x divided by delta t, I get velocity. So in this chapter, what we are going to do is, we are going to assume the motions to be small. Now there is a strong reason for assuming this motion to be small. Now what I want to do is, I want to give you an example. Consider that you have an articulated robot arm. So what you have is, this is the first link, and here is the second link. So this robot arm has two links. So you have link 1 and you have link 2. Now individually, these links can rotate by angle theta. So this is theta 1, and maybe this is theta 2. This is theta 1 and this link is theta 2. Now it is very important that we use the right sequence of rotation, because the large rotations, I need to write this down, large rotations are not commutative. What it means is, if you rotate around X and then you rotate around Y, you get certain orientation. However, if you rotate around Y by the same amount and then you rotate about X, is not going to be the same. So in this particular case, if you orient by some angle theta 1 and then you orient by some angle theta 2, the orientations will be different if the sequence was inverted. So I need to write this down. And what this means, just a second, I think I need to go back. So what it means is, if you consider the rotation, so consider that we have X, Y, and Z. So this is X, this is Y, and this is Z. Now, if you have the rotation, if you have a rotation about X, theta X, and then what you do is, after the rotation, you have a rotation about Y, and I'm gonna call this rotation about the modified or the new Y. So this goes something like this. So X, Y, and Z. We take this up, X, Y, and say Z is here. I will try to show it like this. Then if you have the rotation about theta y, please note these rotations are not commutative, which means rotation theta x about x, then rotation theta y about y is not equal to rotation theta y about y multiplied by rotation theta x about x. So these rotations are not commutative. So the one way to look at it is, even though these large rotations are not commutative, the teeny tiny rotations are. So which means if you rotate by a teeny tiny amount around x, and then you rotate by teeny tiny amount around y, and if you change the sequence, so for an example, now I'm going to rotate by teeny tiny amount around y and then teeny tiny amount by x, surprisingly the answer is the same. So what it means is the large rotations are not commutative, but the small rotations are. And that's what we are going to discuss in this chapter. So the difference between the large rotation and small rotations. So I need to write this down. Large rotations are not commutative, which means the order is important. But small rotations are commutative, which means you can change the sequence of order. Now let's try to understand the concept of what do we mean by the differential motion. So what I'm going to do is I'm going to draw a simple planar robot arm. So consider that we have, this is the first link, and to this first link I have a second link, and then I'm going to add the coordinate system. So in this coordinate system, this is I, this is I, this is J, this is L1, this is L2, and I'm gonna add the values of theta 1 and theta 2. Okay, just a second here. I don't know where it went. recent. So give me a minute here. I will find out where did it disappear. So Dropbox, open. Okay, so we were here. So what I'm going to do is I'm going to draw two links. I will have a link 1 and then I will have a link 2. And then this is going to be angle theta 1. And I'm going to call this angle as angle theta 2. So I have theta 1 and I have theta 2. This is my I, this is my J. So this is my initial position O, and then my final position is say B. So O, A, and B. What I want to do is I want to express this as a vector O to B. So OB is the vector. This also indicates the position of the end effector. So this is the position of end effector. And to find position of the end effector, what I'm going to do is I'm going to have L1 cosine theta 1. Then I will have L1 sine theta 1. Then what I'm going to have is I'm going to have L2 cosine theta 2. So this becomes L2 cosine theta 2. And this becomes L2 sine theta 2. So now you have a robot arm, and this robot arm has the end position, which is B. And what I want to do is I want to find out the end position with respect to the initial position or the initial coordinate or initial frame 0. Now I will write this down as something like this. Position OB can be written as, please note that the unit vector in the x direction is I. Unit vector in the y direction is j. So I'm gonna have L1 cosine theta 1 I plus L1 sine theta 1 j plus L2 cosine theta 2 I plus L2 sine theta 2 j. Any questions here? So this is the position vector OB. So that simply means that if I know the value of theta 1, if I know the value of theta 2, I should be able to find out the value of the final position OB. Now what I want to do is, I want to find out the differential motion. So what I'm going to do is, I'm going to take the derivative. I'm going to take the derivative of OB with respect to time. So when I take the derivative, please try to understand that the derivative of a constant is 0. L1 is a constant. So when I take the derivative, I'm going to get L1 cosine theta 1. The derivative is going to be minus sine theta 1. But please note, the derivative is not with respect to theta 1, but it is with respect to time. So I will have to take the derivative of theta 1 with respect to time. So it will be d theta 1 by dt. And then I will have I. And this is very important. I have used the chain rule. So I'm using the chain rule. So when I'm taking d by dt of cosine theta 1, what this is d by d theta 1 of cosine theta 1 multiplied by d theta 1 by dt. And this expression is minus sine theta 1 and theta 1 dot. So once you do the derivative, this is what you get. Then next thing is, you have L1 cosine theta 1, derivative of theta 1, which is going to be theta 1 dot, plus you are going to have L2, same thing, cosine theta 2 becomes minus sine theta 2. This is going to be J, sine theta 2 dot I plus L2 cosine theta 2 dot J. So this is nothing but the expression for the velocity of the end effector. Now please understand, there are two things that's going on here. You have a velocity in the x direction and you have the velocity in the y direction. So these unit vectors I, they indicate the velocity in the x direction, and unit vectors j indicate the velocity in the y direction. So you have some velocity in I direction, you have some velocity in j direction. Now what I'm going to do is, I'm going to rewrite the same expression slightly differently. So what I'm going to do is, I'm going to write this expression in a matrix form. And I will tell you how my matrix is going to look like. So I'm going to have velocity of end effector in x direction, velocity of end effector in y direction, that needs to be expressed in a matrix vector form. So I will write this down as something like this. I'm going to have theta 1 dot here, and I'm going to have the theta 2 dot over here. And I'm going to have, so velocity of B in x direction velocity of v in y direction. So in other words, if you follow the way I'm gonna do this, is I can write this down as something like i's and i's together. So I will write this down as L1 cosine theta 1, sorry, L1 L1 sine minus sine theta 1. So this becomes minus sine theta 1. Then I will have L2 L2 sine theta 2, and then I will have L1 cosine theta 1, and I will have L2 cosine theta 2. So if you look at the way we have shown here, that this entire expression, this expression can be written as a matrix vector form, and this matrix vector form is nothing but considered as the Jacobian form, and this guy is called as the Jacobian. So what we did, we wrote the expression for the position. We took the derivative of the position, and then we wrote that matrix equation into some sort of the equation in terms of a matrix and a vector. So if you think about this, these are the joint velocities. So the Jacobian is nothing but a transformation L2. Yeah. Yep. This has to be negative. Yeah. So Jacobian is nothing but the transformation that takes the joint velocities and converts that into the end effector velocities. So this is the meaning of Jacobian in the robotics. But what does the Jacobian mean in actual physical practice? And I just want to tell you what this means mathematically. So think about, you have a function. That function is dependent on two variables. So you have a function that is, example is, that is dependent on two variables. And I want you to look at, I have shown here a function which is a function of theta 1 and theta 2. So function f1 depends upon theta 1 and depends upon theta 2. This is exactly same as the expression that we wrote for OB. So the vector OB is dependent on theta 1 and theta 2. So Jacobian is always with respect to origin 0. So just a second, let me finish this discussion. So F1 is theta 1 and theta 2. Now what I'm interested in finding out is, I'm interested in finding out, and this is an important discussion, is how much this function change with respect to theta 1, and how much this function change with respect to theta 2. So the question, let me write this question down. Now the question is, how would F1 change if theta 1 and theta 2 are changed. So would it change by a large amount? Would it change by a small amount? And one classic example that I usually give is something like, imagine that you have $5, you have $5 and 30 cents. So you have $5 and you have 30 cents. Now, if I give you $1, how much that change is going to be? So clearly you will tell me that, hey, if you were to give me $1, I would land up with $6.30. Now, if I were to tell you, hey, if I were to give you 1 cent, how much that change is going to be? And you will say that's simple, it's $5.31. Now, what it means is the change caused by $1 is much, much greater than the change caused by 1 cent. So for an example, in this function, there are two independent variables. The first independent variable is theta. The second independent variable is theta 2. So you have theta 1 and theta 2. And I'm interested in finding out how much this total function changes with respect to change in theta 1 and change in theta 2. So the idea is very simple. So if I want to find out the total change in theta 1 and theta 2, and that change I'm denoting as delta F1, capital delta F1, then I would write this down as partial of F1 with respect to theta 1 multiplied by delta theta 1 plus partial of F2 divided by delta theta 2 multiplied by delta theta 2. Now, if you spend a minute on this expression, it will automatically make sense to you. So you have a total $5.30. You want to note that if I give you $1, the change is significantly more because the intrinsic value of dollar is 100 times that of cents. On the other hand, if you add just cents, the overall change is significantly small because the cents is 1/100th of a dollar. So Jacobian is nothing but a relationship. Jacobian is nothing but a relationship wherein you have the partial derivatives multiplied by the change in the variable. So this is how a Jacobian of a single variable is written, theta 1, delta theta 2. So Jacobian is used to find out the total change, and the total change is dependent on the change in the independent variable. And this is the exact same problem that we looked at a minute ago, but we derived this expression slightly differently. In this particular problem, I want you to note that we are going to use the velocity relationship. So you have link 1, this is link 1, this is link 2, and what I'm interested in finding out the velocity of B. The expression for the velocity of B can be written as velocity of B is equal to velocity of point A plus velocity of B with respect to A. So please note, this is point 0, this is point A, this is point B. So I should be finding out the velocity of A. Now the velocity of A, I just want to show you what that is graphically. The velocity of A is nothing but this guy. Then velocity of B with respect to A is always going to be the perpendicular to the link, which is going to be this. So what I do is, I can use the graphical approach. I can first draw the velocity of A, which is shown over here. Then I draw the velocity of B with respect to A, which I can draw over here. And that gives me the velocity of B. So what I have is, I have velocity of A, I have, this is velocity of A, this is velocity of B with respect to A, and that gives rise to velocity of B. So that is how you will find out the value of velocity of B using some sort of vectorial representation. Now, the other way to find this out is exactly the way what we have done before. So in the previous case, what we did is we actually wrote out the equation for the position vector, and then we took the derivative of the position vector, and then we landed up with the velocity. And that velocity expression can be represented as in terms of the joint variables. So these are the joint variables or variations, and this matrix is called as Jacobian. So by definitions, Jacobian motion and multiplied by joint differential motions gives you velocity. So at the end, what is the use of the Jacobian? Jacobian is used to find out the velocities of the end effector or velocities of any link inside the robot. Now here is a difference between the way we set up the problem and the way this problem is set up. Now I want you to look at the way this problem is set up and then try to tell me how is it different from the problem that we set up over here. Again, this is the two link problem, but you observe that my Jacobian expression is different for the same two link problem. Can someone tell me the difference between this problem setup and this problem setup? And the key difference here is the way theta 2 is defined, and that is correct. If you look at the way theta 2 is defined in this setup, the theta 2 is defined with respect to I axis. So what I have here is my theta 2 is defined with respect to I direction. So with respect to positive x axis. However, in this problem, if you look at in this problem, theta 2 is defined with respect to this length. So if you look at the first link, theta 2 is defined with respect to orientation of first link. And please note since the way theta 1 and theta 2 are defined differently, my expressions for Jacobian are different. So in this case, my Jacobian involves sine theta 1. So here in this case, the Jacobian seems to be more complex because my theta 2 is not defined with respect to horizontal x-axis, but it is defined with respect to the previous link. Now, same relationship can be derived using the direct differentiation. And this is exactly similar to what we have done before. So xb is nothing but the position of b on x-axis. So this distance is xb. This distance is yb. This distance is xb and distance is yb. And what you can do is you can find out very easily this distance is going to be L1 cosine theta 1. This distance, now please understand, you will need to take both the angles. So this will become L2 cosine of theta 1 plus theta 2. This distance is L1 sine theta 1, and this distance is going to be L2 sine theta 1 plus theta 2. And if you look at what we have here, is that is what the expression is shown. XB is L1 cosine theta 1 plus L2 cosine of theta 1 plus theta 2. YB is L1 sine theta 1 plus L2 sine of theta 1 plus theta 2. And then when you take the derivative, please understand that I have the derivative of L1 cosine theta 1, that becomes minus sine theta 1 multiplied by the derivative of theta 1, which is d theta 1, and I extend the same thing, but then I will have to use the chain rule. And then once I plug these values in, on the left hand side, I have the differential motion of B, I have the differential motion of the joint, and I have the Jacobian. So what this tells me is a very simple concept. If I change the value of theta 1 by d theta, if I change the value of theta 1 by d theta, what would be the change in the position of the end effector? So if I change the value of the joint theta 2 by some teeny tiny amount, what would be the change in the position of the end effector? So that is the question the Jacobian tries to answer. This is the change in joint angle, and this is change in position. So Jacobian is the matrix that relates change in the joint angle to change in the position. Now some of you may ask me, is Jacobian constant? Or the next question is, does Jacobian always have to be with respect to origin? Not necessarily. You could have a Jacobian with respect to some that is defined in a different frame. So Jacobian doesn't have to be with respect to the first frame or second frame, depending upon what your equation is, depending upon what your joint variables are, the Jacobian is defined. The next question is Jacobian constant? Now please understand that this Jacobian, it actually depends. It depends upon theta 1 and theta 2. So the Jacobian depends upon theta 1 and theta 2. So if theta 1 and theta 2 are changing, then the value of the Jacobian will be changing. Essentially, your velocity of the end effector would be changing. And we will take a few examples that will make this concept clear. So this is the reiteration of the Jacobian concept. So consider that we have this two-link robot, and what's happening is we are causing this motion. Now, depending upon how these two arms are oriented, the resulting motion is going to be totally different. For example, if your robot arm is vertical, the rotation theta 1 will cause a different motion compared to when your robot arm is horizontal. So what it means, even though your theta 1 is the same, the matrix, this Jacobian, will dictate how far your end effector is going to move. So the Jacobian actually is sort of a matrix that converts the joint motion, the individual joint motion, to the end effector motion. Now this is the mathematical definition of Jacobian. And I just want to give you a slightly more intuitive definition. Think about it like this. Imagine I have X, Y, and Z. So I have X, Y, and Z. And this is the function which is dependent on, I'm going to call this is Y, this is X, this is Z. So this is the function, Y is the function of X and Z. And I'm going to show this as a surface. So what I'm going to do is, I'm going to show this as a surface. So this is the function, and it's actually a surface because it depends upon X and depends upon Z. So if I want to show how it varies with respect to Z, I'll draw lines which are sort of parallel to Z. If I want to show how this changes with respect to X, then I'll show lines which are parallel to X. Now here is my question. The question is, and this is an important question, I am at this location. And this location is A. And I want to go to location B. So I want to go to location B. So I'm at location A and I want to go to location B. How would this change be characterized in terms of mathematical expression? So I am at A. So I am at A and I want to go to Y at B. How can I find this change? So clearly what you will do is you will say whatever value you have at Y, so Y of B, you can say, hey, if you're at Y of A, then you will find out how much change you have in the X direction. So basically you will have in X direction, multiply that by delta X, plus you have change in the Z direction, and then multiply that by change in the Z direction. And this exactly is representing the change uh, when I go from y of a to y of b. So by definition, I can write this down as if I am at location A. If I want to go to location B, then I am interested in finding out the change in the magnitude of function with respect to x-axis, change in the magnitude of function with respect to z-axis, and then I multiply by the respective differences. And that is what is the meaning of the Jacobian, which is exactly similar as something like this. Think about it, like you have again a slope, and this is the x-axis. So if you want to find out the change in the y direction, you multiply the slope by the change delta x. So if you have the slope s, slope multiplied by change in the x will give you change in the y. But the difference in Jacobian is now it's not only dependent on x, but it is dependent on y, it's dependent on z, and so on. So I'm interested in finding out the change in the function when the individual components of the function they change. And Jacobian is the mathematical representation indicating that change. And now this Jacobian can be arranged into the matrix form, wherein deltas are the changes in the function, change in function, and this is change in the independent variable. So if you want to find out the total change in the function, you will have Jacobian multiplied by change in the independent variable. Now let's try to get to the robotics. Where is Jacobian used in robotics? So for an example, let me give you, if you have a 6 degree of freedom robot arm, say, let's assume that you have a 6 degree of freedom robot arm. So it's a 6 DOF robot arm. And this 6 degree of freedom robot arm has different values like theta 1, theta 2, theta 3, theta 1, theta 2, theta 3. So I'm interested in answering this question. How is the motion of the robot arm dependent on theta 1, theta 2, all the way up to theta 6? So what this Jacobian tells me is if I substitute the teeny tiny change in the value theta 1, how would the final position of the robot arm change? As you can see, if I have change in theta 1, that becomes delta theta 1, that changes the final position of the robot arm. You can see it like delta x, delta y, delta z, small delta x, small delta y, small delta z. So this Jacobian allows me to relate the change in the joint angles with respect to the change in the gross motion. Now, here is a very simple example of the differential versus large scale motions. Now, think about it like you have a robot car, and what you want to do is there are you want to travel by distance L and you want to rotate by angle theta. So here are two things. We want to travel by distance L and we want to rotate by angle theta. Now in the first example, in here, you would note that first I'm traveling straight line in L and then I'm rotating. So I travel in a straight line and then I rotate. But now here, please observe that in case B, I rotate by theta and then I travel by L. Now clearly the position, the end position that is achieved in case A is different than the end position that is achieved in case B. So whatever if we initially travels by distance L and then rotate by theta, the end position is different if I were to rotate by theta and travel by L. But now what happens if the motion is differential? Now what do I mean by motion is differential? Which means I'm going to travel by small l and then rotate by small theta. I'm gonna travel by small l and I'm gonna rotate by small theta. So you will observe that when I'm using these teeny tiny motions, it really does not matter whether I first change the orientation and then travel, or first I travel and change orientation. So with this, my final condition, which is point B, the final condition is going to be the same, because now my motions are differential, my motions are small. So differential motions are commutative. So in the last case, which is case C, it does not matter if I rotate first and then travel later, or I travel first and rotate later, my end position is going to be the same. Now differential motions, they are basically, you could have a differential motion defined in a frame, or you could have a differential motion of the robot arm itself. So now there are multiple ways of looking at this problem. So in theory, what you could do is you could look at the differential motion of the frame separately. So you can look at the rotational motion of the frame, translational motion of the frame, and then you can use those concepts to solve robot problem. If you look at the way the textbook discusses it, textbook is going to look at frame motion, pure translation, pure rotation, and then you will have the robot motion. So let me give you the theoretical part, and please understand that these concepts are not difficult. As a matter of fact, they are super simple. And when we work out the problems, these concepts will be very clear to you. So for next couple of classes, we are going to work out the problems on Jacobian, differential motions, and so on. So it will be very clear what these differential motions mean, how do we solve the differential motions problem. But from theoretical point of view, so there are two preliminary concepts. One is a differential translation, which means you are translating along x-axis, y-axis, or z-axis. And you have differential rotation, which means you are rotating about x-axis, you are rotating about y-axis, you are rotating about z-axis. And what you could have is, you could have something called as the differential transformation, wherein you are translating and rotating together. So if you have just the prismatic joint, you will typically have differential translation. If you have a revolute joint, you will have differential rotations. But if typically in the robot, you will have a prismatic joint and revolute joint. So you will have a differential transformation that combines translation and rotations. Now, what are differential translation? Differential translations are simply small motions about x-axis, y-axis, and z-axis. And whenever I talk about the frame differential translation, which means I physically take that frame and translate, move around, about x-axis, y-axis, or z-axis. And dx, dy, dz are the distances that are used for translating that frame. Now, what do I mean by differential rotations? Differential rotations means, suppose if you have a coordinate system x, y, and z. If you have a coordinate system x, y, and z, you actually rotate about x, about y, or about z. But please note, these rotations, they have to be small. They cannot be super large, because differential rotations implies that these rotations are very small so that they can be treated as commutative rotations. Now, I will give you a simple trick when we look at the differential rotations. So whenever you are looking at the differential rotations, since the angles are very small, sine theta is approximated to theta and cosine theta is approximated to 1. So since the differential rotations are small rotations, sine theta is approximated to theta and cosine thetas are approximated to 1. What it means is usually these angular rotations are about 5 to 10 degrees, because sine theta is equal to theta in radians and cosine theta is equal to 1. These equations are valid, these relations are valid when the angles are less than 17 degrees. Now here comes the big matrix. So these are the differential rotation matrix. They may look intimidating, but the concept is very simple. If you look at in the last class, we looked at the rotations about x, y, and z. So let me give you a simple concept. So if you have, and we know all about this. So this is x, this is y, this is z, and this is the rotation theta. And how does the rotation matrix for rotation about z looks like? So rotation about z can be written as cosine theta minus sine theta, sine theta, cosine theta, 0, 0, 1, 0. So that is how the rotation looks like. So the rotation cosine theta, sine theta, minus sine theta, sine theta, cosine theta. Now I want you to make this change. Cosine theta is equal to 1, sine theta is equal to theta. And please note that this rotation is shown over here. So cosine theta becomes 1, minus sine theta is minus theta, sine theta is theta, cosine theta becomes 1. So differential rotations are nothing but the rotation matrices. Differential rotations are nothing but the rotational matrices wherein sine theta is replaced by theta and cosine theta is replaced by 1. And I need to write this down. Differential rotations, rotation matrix where cosine theta is replaced as 1 and sine theta is replaced as theta. Now let's quickly, I want you to look at quickly this rotation about x. And you would notice when we look at the rotation about x, the rotation matrix is given as 1, 0, 0, 0 cosine theta minus sine theta, 0 sine theta cosine theta. So now I want you to note that if you substitute cosine theta is equal to 1 and sine theta is equal to theta, or in this case delta x, you will get the differential rotation matrix that is shown on the right hand side. So that is what it means by differential rotations about the reference axis. So differential rotations are nothing but the rotation matrices wherein the sine theta is replaced as theta and cosine theta is replaced as 1. Now, one thing I want to clarify here is when you have multiple rotations, what happens? Now, this is the concept that we discussed earlier. So when we have multiple rotations, so say if you have rotation about X and then you have rotation about Y, typically these rotations are not commutative. And why aren't they commutative? And the reason they are not commutative, because I want you to note that there is a product term over here. So you have the product term, which is delta X, delta Y. Since you have this product term floating around, this motion is not commutative. However, if you ignore the product terms, and when would you ignore the product terms? Think about like your delta x is 0.1 and your delta y is also 0.1. So their product is going to be 0.001, which is very close to 0. So you actually ignore it. So if you ignore the product or the higher order terms, you will realize that these rotations, which is rotation x, rotation y multiplied by rotation x, give you one and the same answer. And this is an important point, and I would emphasize this again in next class. So whenever you have small rotations and you ignore the product terms, what you land up with the same answer. And this is the expression for the differential rotation about a general axis, which means if you have an arbitrary axis and say I'm interested in finding out the rotation x multiplied by rotation y multiplied by rotation z. Again, let me say that one more time. Differential rotations are nothing but rotation matrices with sine theta is equal to theta and cosine theta is equal to 1. So once you make this substitution, carry out this matrix multiplication, you will land up with this big expression that indicates the differential rotation about the general axis. Okay, I'm gonna stop here. And in today's class, we looked at a lot of theory, but please don't let this theory scare you or confuse you. When we start solving the problems, and we'll solve a lot of problems, all this theory will make sense. So next class, I will actually work out the robot problem where we will find out the Jacobians and then we will use MATLAB to solve the Jacobian problems. So I'm gonna stop recording and I would be happy to answer any questions that you may have.